Hello friends, today I will discuss the locus diagrams. Here I will cover the definition of that locus diagram, necessity of the locus diagram, and how we use that for a general RLC series circuit. Then how the admittance diagram will look like, and then how we can apply that for the various circuits. And also this is necessary to know whether the circuit is going to resonate with the available elements in the circuit or not. If it is going to resonate, does it going to resonate with one inductor or with two types of or two values of inductor or two values of capacitors, means at two places, etc. we come to know with the help of locus diagrams. So coming to the definition, it is the expression of phasor diagram with change in frequency or change in the resistance or change in the inductance or change in the capacitance with respect to the voltage. So let us take a RLC series circuit like this. Here inductance is fixed, resistance is fixed, capacitance also fixed, applied voltage is also fixed, but the supply frequency is going to change. In that case, we see that what are the impedance or reactance of these elements, how they change with respect to frequency. Let us say the inductive reactance definition or the expression is nothing but omega L. Similarly, for the capacitive reactance, the expression is 1 by omega C. That means if the supply frequency increases, the inductive reactance value increases. Whereas the capacitive reactance starts reducing with the increasing frequency. And here for our analysis, we say the difference of the inductive reactance and the capacitance we represent with X. So that may become negative or that may become plus. If it is plus means the inductive reactance is dominating in the circuit. If it is negative means it is the capacitive reactance dominating. So for this circuit, let us write the impedance, that is Z is equal to R plus J into XL minus XC. So that we can write R plus J into X. Omega is variable, means supply frequency is variable. Then once we know the Z, we can write the what is called the admittance. Admittance is nothing but the inverse of impedance, that is 1 by Z. So that 1 by Z we can write as G plus JB. G means conductance, B means susceptance. That is equal to 1 by R plus JX. So this R plus JX is nothing but Z. And multiplying both numerator and denominator with R minus JX of Y, then we get like this. R minus Jx divided by R plus Jx into R minus Jx. Once we simplify it and we separate the real parts and the imaginary parts, we get like this. R by R square plus X square minus J into X divided by R square plus X square. This we can further simplify as like this. G plus JB. So where G means conductance, it is given by R plus R divided by R square plus X square. Similarly, susceptance B is equal to X divided by R square plus X square. And we say this is equation 2 and this is equation 1. And if you look at this, or is anyhow constant, whereas G and B depends upon the supply frequency. From equation 1, we can write G by R is equal to 1 by R square plus X square. On squaring the equation 1 and 2 and adding them, we get the equation like this. G square plus B square is equal to R by R square plus X square whole square plus minus X divided by R square plus X square whole square. So if you further simplify, we get like this. G square plus B square is equal to R square divided by R square plus X square whole square plus X square divided by R square plus X square whole square. Because the denominator is same, we can add the numerators like this. R square plus X square divided by R square plus X square whole square. And if you look at this, so 1 x square plus x square in the denominator going to get cancelled with the numerator value. Then we get G square plus B square is equal to 1 by R square plus X square. So as we know from equation 1, that is 1 by X square plus R square is nothing but G by R. So we substitute here. Then we get G square plus B square is equal to G by R. Then bring that to the left side. Then we get like this. G square plus B square minus G by R is equal to 0. Then this we can write equation like this. That is G minus 1 by 2R whole square plus B square is equal to 1 by 2R whole square. And this is nothing but a form of circle. Means this is a circle with the center as 1 by 2R and 0 and radius is 1 by 2R. And if we draw that circle for this admittance Y, we get like this. Admittance has the two parts. One is the conductance, the other is susceptance. So conductance is a real value. So we draw a circle with 1 by R ratio, 1 by 2R radius with center 1 by 2R 0 like this. Then we get a circle like this. If you look at this, as omega increases, inductive reactance increases. That means XL is more than XC in this region. Whereas here, the capacitive reactance is more than the inductive reactance. So that means whenever we have a only inductance variable, then we get the one half circle. Suppose we have the variable capacitance, another half circle, means semicircle we get. This is going to be used for our circuit analysis in the coming lectures. So before we apply this admittance analysis, let us see how the VI relations exist for a resistance, inductance and capacitance, and then we apply that locus diagram technique for the real-time problems. So for a resistance, if you apply the voltage and current flows, then in that case voltage and current are in phase with each other, and if you see the waveforms, they look like this. This is voltage waveform and this is the current waveform. Both are in phase with each other. Similarly, in an inductor, the reactance is given by omega L and the inductive impedance is represented by J into XL. And when we come to its VI relations, so in an inductor, voltage leads the current by 90 degrees like this. This is the current vector and this is the voltage vector. Voltage leading the current by 90 degrees. And if we see those voltage waveforms, then we get like this. Voltage is leading whereas the current is lagging by 90 degrees. and this is the applied voltage to the inductance. Similarly, when you go to the capacitor, so capacitive reactance is represented by Xc, that is equal to 1 by X omega C, that is also is equal to 1 by 2 pi Fc. And coming to the capacitive impedance, we represent with Zc, then we get 1 by j omega C, and if you further simplify it, that is multiplying both numerator and denominator with j, then we get minus j into Xc. And coming to the Vi relation in the capacitor, voltage leads the current leads the voltage by 90 degrees. So this is the ideal capacitor, applied voltage is V and the current flowing is IC, and if you look at this, current is leading the voltage by 90 degrees, and if you draw the vector diagrams, we find like this: current is leading the voltage vector by 90 degrees. So having known this idea, so let us apply to the circuits where we find the one element is varying with respect to time or with respect to frequency. So if you look at this, this is the RL series circuits connected to a AC supply where the inductance is varying. Means inductive reactance is varying. So in that case, so there are two possibilities for the current. If this inductive reactance is 0, in that case the current that flows in the circuit is maximum. So that means the circuit becomes a pure resistive circuit. In a pure resistive circuit, voltage and current are in phase. So remember here, whenever in the locus diagrams we have the variable element, so make it that to 0, then see the voltage and current relation for the circuit, and that will become the starting point of the current for the locus diagram. So in this case, resistor is fixed and inductive reactance is variable. So first put 0. Once we put XL 0, in that case resistance is there. So the current that flows is V by R, and that we call as maximum current. Because it is a resistor and the current flowing in that is in phase with the applied voltage, so we draw the current vector in phase like this. This is the maximum current that flows in the circuit and given by V by R. Suppose if you make the inductive reactance infinity, in that case no current flows in this circuit, means you will get this point. Suppose the inductive reactance is more than 0 but less than infinity, in that case, so we get the R value and L value presents. So means in a inductor, the current lags the voltage by 90 degrees. But whereas in a resistor, current is in phase. So the resultant only will flow through the circuit. So once the XL is increased, then we get the current somewhere here, means more inductance. Means this at XL is 0, we get this. If the XL is increased more than XL 0, then we get the current vector here. If you further increase the inductance, then we get the current resultant current here. If you further increase, you will get the current like this. So if you further increase the inductive reactance, so it will trace the current vector in the form of a semicircle with respect to the voltage axis, and finally reaches 0 when the XL is equal to infinity, like this. That we can see here also. XL is equal to 0, maximum current is Vm by R, V by R. And other cases, current I is equal to Vm by R plus j omega L. So that is what this will show, current path. And next, coming to the RL circuit with variable resistor. So whenever we have the circuit like this, first thing that we have to do is draw the voltage vector position and also current vector position. Then next step is make the variable component value 0. So in this case it is resistance, make it to 0. Then the current flowing is pure inductive current. So in a pure inductor, current lags the voltage by 90 degrees. So find out what is that current. That is V by omega L or Vm by XL. So this is the current flowing in the pure inductor, means the current lags the applied voltage by 90 degrees, means that will be here, and that value is also maximum in this circuit. So we get maximum current here. This is the position, first position. So this we have to fix it. So once this is fixed, then go to the R is equal to infinity. If the R is infinity, the current that flows in the circuit will become 0, means that current instead of here it comes here, that is 0 value. And in between, suppose the resistance value is not 0 but it's something more than 0, in that case, so we find the resultant current flowing in this circuit, it will be like somewhere here. Then if we increase the further resistance, we get value here. If you further increase the resistance, we get like this. So if you further increase, we get here somewhere here. If the resistance value increases, means automatically the angle between the resultant current and the applied voltage starts reducing. So once that R becomes infinity, the current becomes 0 like this. Next, suppose we have the RC circuit, series circuit with variable capacitance like this. So in this case also, first thing which we have to do is first make that variable element reactance equal to 0, that is XC is equal to 0. Then find out what is the current flowing. So then we get here V by R. So that V is nothing but maximum voltage, that is Vm divided by R. So what is this current? This is the current due to the pure resistor. So in a pure resistor, the current and voltage are in phase with each other. So to draw the locus diagram, first to draw the voltage vector and current vector, and then fix up the current vector with respect to the voltage vector. This is the voltage vector. At Xc is equal to 0, the current flowing in the circuit is V by R, that will be maximum current. Because it is a resistor, that will be in phase with the applied voltage like this, that is V and I are in phase, and that I is maximum value. So if we increase the capacitive reactance instead of 0, then the angle between the voltage and the current increases, that too current leads the voltage by some angle. So if you further increase the capacitive reactance, the resultant current comes here. If you further increase the Xc, it will come here. Means the current starts leading the voltage as the Xc increases. But once Xc becomes infinity, the current flowing in the circuit will become 0. So means that ends up like this. Means it will become like a semicircle with respect to the applied voltage. So let us see another circuit, RC circuit with variable resistance. So look at this. This is the applied voltage and this is the capacitor and this is the variable resistor. So here also the first step is draw the voltage vector and current vector like this. Next step is, so make the variable element impedance equal to 0. Then find out the current flowing in the circuit. That will become the maximum current in the circuit. That is R is equal to 0. Maximum current will become V by XC like this, that is Vm by XC, means it is the current due to the pure capacitance in the circuit. In a pure capacitor, current leads the applied voltage by 90 degrees. So this position has to be fixed with respect to the voltage vector on the locus diagram. This is the voltage vector, and we have calculated the current flowing when R is equal to 0, that is equal to V by XC. So in a capacitor, current leads the voltage by 90 degrees. So we get like this, and that value is V by XC. So if you start increasing the resistance and if you make it to infinity, in that case the current flowing in the circuit will become 0, means it comes here. Suppose the resistance is more than 0 but less than infinity. So if you look at this, if the resistance increased, so the resultant current comes here first, then comes here, then comes here, means the angle between the applied voltage and the current resultant current flowing in the circuit becomes lesser and lesser, means goes on decreasing. So let me summarize once. We have seen what is the importance of the locus diagrams for the networks, and we have seen with RLC series circuit how the admittance diagram looks like, and we have seen how the voltage and current are related in the inductor, capacitor and the resistor. And next we have seen how the voltage and current vectors or the locus diagrams varies when the elements are changed with RL series circuit, with RC series circuit, where once we change the resistance and once we fix the we changed the inductance. Similarly, in another case, we changed the resistance once, keeping the capacitance fixed. In the other case, we changed we start varying the capacitance while the resistor is fixed.